sorry, I don't know whether we
Okay.
maybe are we ready?
Yeah, you can start. I just need to fix the battery.
So should we start or?
Yeah, you can start.
Okay, we are very happy to have Suvrat Raju from ICTS, who's going to tell us about gravitational subalgebras in holographic systems.
Okay, first I should thank my co-organizers, especially Vishnu, for getting us to this really wonderful place. We've been thinking about this meeting for a long time, so I'm glad we managed to pull it off. And it's really nice to be back here. Thank you all for coming, despite rather hectic morning, staying up for this talk. So I'm going to talk about, this title is actually somewhat tentative. I'm going to talk about work in progress with Anthony Speranza and Christian Jensen. And hopefully the paper will be out in a couple of weeks. But some of what I'm saying is still tentative because it's still work in progress. So I'd be happy to receive feedback, and please also be a little cautious about some of the formulas that I write. So since this is a short talk, I'm going to try and give you just the basic idea of what I'm about to say. And I'll try and keep the technical details to a minimum, but I'm happy to discuss them offline. So the basic theme of what I'm going to talk about is the following. So there's been a lot of work recently in trying to define von Neumann algebras and trying to understand von Neumann algebras in theories of gravity. Now, frankly speaking, I know very little about von Neumann algebras. So the way some of this project started with just my simple-minded confusion about some of the results that had already been obtained, in particular by Sorce, Speranza, and Jensen. So this is I'm not going to take a very sophisticated mathematical perspective, but just try and ask some basic physical questions. So the physical question that we want to ask in this talk is the following. So imagine that you're in a theory of in an asymptotically anti-de Sitter space, a theory of gravity in asymptotically anti-de Sitter space. So the question that I want to ask is, does it make sense to define an algebra in the gravitational theory for some time band? Can you see? Can you all see at the back as well? For some time band on the boundary that goes from minus t by 2 to t by 2, which is smaller than the light crossing time of AdS. Okay, so the light crossing time of AdS in some units is pi, maybe this is minus pi by 2. And the question is, does it make sense to define?
You can write a little bigger.
Okay. So can you this is minus pi by 2, pi by 2, t, I'll write it from now. So the question is, does it make sense to try and define such an algebra for the time band in a theory of gravity? So physically, what are we trying to do? What we are trying to do is the following. Let me draw the picture again, slightly bigger. What we really want to define is the time band is an algebra in the bulk that corresponds to this region and its complement. So this algebra of the time band we want to think of as belonging to this region R bar in the bulk, which I'll specify in a minute, and its complement or its commutant as belonging to a diamond in the center, which is R. So the question is, how do we define? So how do we define these algebras in gravity? Okay, so the first thing I have to tell you is why this is even a question. Okay, so you might ask, maybe you just take all the operators and you think of the algebra as you usually do. So why is there even a subtlety? So I want to tell you that there is a subtlety in defining these algebras. And I want to then tell you how to resolve the subtlety. And this resolution of this subtlety has to do with older techniques of how to define local operators or quasi-local operators in theories of gravity. And so this has to do with quasi-local operators. And then I want to tell you how, when you resolve this subtlety that I'll explain in a minute, and try and use these old formulas which have been around from the time of David, in fact, for how to define local operators in gravity, this in fact leads exactly to these formulas for these cross-product algebras that have been explored recently in the literature. So I'm going to try and establish a link between these older formulas and this newer work that has been explored extensively in the literature. Okay. So that's an outline of the talk. Okay. I hope the question is clear, and the main points I want to make I'll explain. But the question is, how do you define an algebra for this time band in a theory of gravity? It might not be obvious to all of you why this is a question that's interesting or that's subtle. But so the first thing I'm going to try and explain is why this is a subtle question. And I'll explain how to resolve this subtlety. And the resolution of this subtlety will make link with some older formulas for how to define quasi-local operators in gravity. And then I'm going to tell you that these formulas happen to be exactly, although a link which has not been noticed so far, the same as the formulas for the gravitational cross product that have been studied extensively in the recent literature.
Is the quasi-local operator story the same as dressing?
The quasi-local operator story is similar to dressing, but yeah, so I mean, of course, that's one way of saying, these cross products come from dressing in a way,
Yeah.
but it's a little more precise than that. So there's some, I'll try and write down some precise formulas for how you dress. So indeed, you have to introduce an observer and dress to the observer, but there's some details of how to do that, which give you exactly the cross product.
Sorry, at a very naive level,
Yeah.
what is this algebra acting on?
This algebra,
Does
so
it
I
have
have to
the
define
space
Hilbert
or-
space. Right now, this is just an algebra of observables. So I want to ask, what is the set of observables that's restricted to the time band? It'll act on the Hilbert space of the theory.
Are these observables of the boundary theory?
These observables, I'll specify that as well. The whole thing can be thought of as observables in the bulk theory, but taken to the boundary. So I'll say that.
This is asymptotically AdS.
This is asymptotically AdS. In fact, for the purpose of this talk, you can think of the whole geometry as just being EDS everywhere. Although what I say will generalize immediately to asymptotically AdS geometries, which are not just AdS. But in fact, in this talk, I'm happy if you, in the approximation which I'm working, in which you just imagine the metric is everywhere totally AdS.
And can this question, as Kosovo was saying, be thought of as a boundary question?
It can be thought of as a boundary question also, yes.
And this time band, when you say time band everywhere in
Time band
space,
everywhere.
so if it were a small part in space,
Then there's no sun.
then you could do that. But from the boundary point of view, then it looks like
Exactly.
it cannot quite restrict to a
Good.
time band
So-
because you just have to do
Exactly. Good. So that's the subtlety. So I'll come. Exactly. Thank you. That's the subtlety of immediate anticipated, but which I will explain. Yes.
The overall goal is to understand something about what? About quantum gravity? I mean, just as
The overall
coming from
goal is to
lower.
understand how you define an algebra for this region in the theory of gravity and the complement of the region in theory of gravity, which is the same in fact as asking how do you define the algebra for the time. So you want to ask, how do you define algebras for subregions in gravity? Can you define that? And what is the structure of these algebras? So what is the structure of the set of observables that you can associate with subregions?
some subregions you can, right?
With some subregions you obviously can. For this subregion there's a subregion. You're anticipating step 2, so this can follow.
Suvrat, this kind of a time band is exactly what you looked at for this holography of information.
Yeah, this kind of time band is exactly.
Does this certainly affect the proof?
Yeah, well, it doesn't affect the proof, of course. No, the proof is correct. It's also this relation. So give me a minute. Let me at least say the subtlety, and and I will answer all of these questions as we go. Okay, good. So let me try and make this precise. In fact, the business of making this precise is just answering the questions. Let me start by first explaining to you how you would define these algebras in a theory without gravity. Okay. So let's say I had this question which will help to explain what the subtlety is. So let's say I first thought of a theory without gravity. So this is some quantum field theory in anti-de Sitter space which does not have gravity. Then it's very easy to define these algebras. And how do I define them? Imagine you have some matter field, okay, some scalar field, phi, which can be any field, doesn't have to be a scalar field, but I'll take it to be phi. And this is some local field in the bulk. This is time, this is the sphere in AdS. And I take the limit. And this gives me an operator on the boundary, which is labeled by a boundary time and a boundary point on the sphere, on the boundary sphere. Okay. Then I just consider the set of all operators that live in this time. So I take these operators and I smear them. Okay, so this is O of f. I also have to smear an omega, okay, along the sphere, but that's actually a pretty uninteresting smearing. I can smear with any spherical harmonic, and since I'm writing on the board, I'm going to suppress the omega direction. Okay. So I'll just take care of the t direction. There is in fact really an omega and an omega, but if you can't see it, it doesn't matter because I want to suppress it anyway. Yeah. Okay, good. So I take this OF and then I define the algebra, which is just, the span of O of F1, O of F1, O of F2, and so on, all the way up to infinity. So these are all the operators that live in the timeline. That's it. Okay, I'm done. That defines for you in the theory without gravity the algebra of the timeline.
Span of the generator.
The span
Algebra
of,
generated by these or span of this?
well, you take, so I wrote down all polynomials, so now you just have to take the span. Because I wrote down all polynomials up to infinity. So I wrote O of F1, O of F1, O of F2, O of F1, O of F2, O of infinity. So this is the set of all polynomials. Of course, when you define a polynomial algebra, this is not enough. You actually have to take bounded functions of these polynomials. Okay, but I won't bother doing that. This is the set of all polynomials. You put them in bounded functions. I'll give you a polynomial algebra. Okay, and this algebra is the algebra that corresponds to the timeline. So if I was working on a theory without gravity, this would be the end of my talk. It would be even shorter than 45.
Sure. So, one question: what is the point of this smearing function?
You have to smear the operators to make them. That's just a way of making them slightly smooth.
Okay.
You smoothen the operators to get operators which are not singular, which have nice fluctuations.
And all these f's, they form some kind of vector space.
These f's are just normalizable. I don't have to take these f's. I can take the binary.
So what determines the maximum number of f's?
Nothing determines the maximum number of f's is infinity. So I have to look at all polynomials. But these f's I just introduced to smoothen things. I don't even have to write the s. I could write O of t1, O of t1, O of t2, O of t1, O of t2, O of tn. I just smeared it a little bit too, because you need to do that too.
So in principle, you can take any like a vector space of
You can take a vector
functions.
space. It is a vector space. Space.
So can equivalently also consider the ring region
Yes.
in the bulk?
As I now just want to explain. Yeah. So as Abhijit is anticipating, this algebra has an actual bulk interpretation. What's the bulk interpretation? The bulk interpretation you consider this annular region that extends from R is equal to cot t by 2 to infinity. Okay? And if you consider this annular region, so this is R which looks like an E, this is my R. So this R which means the radial direction, which goes from cot t by 2 up to infinity. And if you do that, you can put these operators that we have written down in one-to-one correspondence with all bulk operators that go from here to here and this causal completion of this region. Okay? So specifically, the statement is, if you look at phi of r equal to 0 omega in the bulk, then you can reconstruct it as some HKLN formula that tells you that you can write it as O of t prime, K of t prime, t prime. And there's also an integral over omega. This formula that I wrote down is actually slightly deceptive. If you really try and go into the details, you'll find you cannot write down the formula in position space, you have to write down the formula in momentum space, but that's a subtlety that's not important for the purpose of this talk. It has to do with the fact that this guy is actually a distribution. It can only act on certain kinds of distributions, it can only act on certain kinds of functions, it's a distribution, not really a function, but that's not a subtlety that's important for this talk. But physically, the point is simply that if you think of the bulk field, for this value of r between cot t by 2 to infinity, on the t equal to 0 slice, you can reconstruct it in terms of the boundary field. Okay? Forget about it. Okay, therefore, this algebra that we wrote, you can also think of as the algebra of this region. What is the commutant of this algebra? The commutant of this algebra is the algebra of the bulk causal diamond. How do you write the commutant of the algebra? Well, there's a HKLN formula. This integral goes from minus t by 2 to t by 2. Correspondingly, you can write phi of r equal to 0 at any value of r as O of t from minus pi by 2 to pi by 2. This is the different k or k delta. And this is valid for any value of r. So this is just a standard HKLN kernel that tells you that if you integrate over the whole light crossing time, then you can also reconstruct fields in the bulk. If I take this set of operators and I restrict them to phi to r smaller than cot t by 2, here it was r larger than cot t by 2. If I take this set of operators and polynomials in these, then this algebra is the commutant of the time band algebra. Okay, so this is the answer to the quantum field theory question. It's kind of a very simple answer, right? And it's very explicit. So let me just say what the answer is. The answer is you just take all operators here, you just multiply them in all possible ways, you get polynomials, you have to smooth them and put them in bounded functions. Not very important for the physics of what we are talking about. That gives you the algebra of the time band. The algebra of the time band is the same as the algebra of this angular region and its causal completion. So this is what's called a causal wedge. The commutant of this algebra is the algebra of this bulk causal diamond, which is constructed by thinking of r smaller than cot t by 2. Okay. And how do you construct it? Well, you integrate now the boundary field over all time, minus pi by 2 to pi by 2 with some different kernel. You take these operators and then you restrict the coordinate here to be less than cot t by 2. Okay, that gives you the commutant of this algebra. Okay. So that's the answer for what's the algebra and its commutant in a theory without gravity. Okay, so there's no subtlety, it's all very explicit.
Sorry,
Yeah.
why are you not using O of F1, etc. later on?
So here I already smeared this.
So that is actually O of F of t.
Well, sorry. So O of f of t was just something I did to smoothen the operators.
Yeah, but you are no longer using them after that.
Well, there I'm talking about the commutant. That's a different algebra. So on this side I have the commutant. On this side I have the algebra. So these operators have the property that they commute with all of those O's. If I take one of these O's, then these commute. This is the commutant of the algebra. This is the set of all operators that commute. In fact, I should smear these operators and put them in bounded functions as well. Cannot work it. Okay, good. So that's the answer to the quantum field theory. Now, why is there a subtlety in a theory of gravity? As you anticipated, as some of you already anticipated, if I try to extend this whole construction that was so simple in quantum field theory to a theory of gravity, I'll find that things don't quite make sense. Why don't things quite make sense? For the following reason. In a theory of gravity, what happens? Well, first of all, apart from the scalar field, you also have to think of transverse traceless gravitons.
Sorry, Suvrat,
Yeah.
another question.
Yes.
On the left hand side, you said t equal to 0,
Yes.
right? And on the right hand side,
I have t on all. That's correct. So this
you are
is
integrating over t prime,
that's right.
but why are you not setting t equal
I
to
should
0 on
set
the
t.
right hand side?
I should.
Okay.
Okay. So what is the problem with theory of gravity? So in theory of gravity, what happens? There are two effects. First, with gravity now, you need to have transverse traceless gravitons. So I can't just continue to work with a scalar field. In fact, just introducing transverse traceless gravitons is not a big deal. I just have to add some indices and I write down the same formulas that I wrote down previously. However, there is a more interesting effect which has to do with the fact that one component of the graviton gives you the Hamiltonian. Okay? So after some factors of G Newton, if you look at and you look at the TT component of the graviton and you integrate this over omega, this guy is the ADM Hamiltonian in the Pfefferman-Graham gauge. Okay, in the Pfefferman-Graham gauge where I said HR mu is equal to 0. And this is the fluctuation, this is not the metric, but it's the metric fluctuation. If I look at the metric fluctuation and I integrate it on the sphere in a particular gauge, just the integral of the metric fluctuation gives you the Hamiltonian. This is dual to the fact that the integral of the boundary of TTT is the Hamiltonian. Okay, so you take the stress tensor, take its 0, 0 component, and you integrate it, you get the Hamiltonian. Okay, so this is just the fact that this extrapolate dictionary gives you the stress tensor. Now, having it so, in particular, one of the elements of the time band algebra in a theory of gravity is the Hamiltonian. So the Hamiltonian is also one of the elements of the time-band algebra. But now you're in trouble because the algebra must be closed under products. I mean, that's the definition of the algebra. But now you find if the Hamiltonian is an element of the time-band algebra, then I can take O of tau and this gives you O of tau plus x. And in particular, even if mod of tau is smaller than t by 2, since this operator is an element of the algebra for all values of x, it's clear that mod of tau plus x doesn't have to be smaller than t by 2. So this tells you that if you try to close this algebra, if you take a set of operators in a time band and you try to close it, you'll be in trouble because you will find that you can use the elements of the algebra and use products within the algebra to evolve outside the time band.
So what's the range of x?
The range of x is anything, it's arbitrary. This operator is always an element of the algebra because the Hamiltonian is an element of the algebra. So I can always take products. This is an element of the algebra. This is an element of the algebra. This is an element of the algebra. But once I took a product, I evolved out of the time band. Now you might say, well, this is a formal formula, I don't like it, and so on. But in fact, this is not a formal formula. In these arguments where we looked at holography of information, we've analyzed different versions of this formula. And in particular, this is actually a very physical formula. If you just allow me to sit at the boundary, and if I think of empty AdS and excitations about empty AdS, I can really do physical processes on the boundary that will let me extract operators and information about what is here. So therefore, this kind of argument and these other arguments that are related to holography of information suggest that in a theory of gravity, the time-band algebra is the full algebra. It's a set of all operators. So in gravity, the time-band algebra has no commutant. Okay. So this is what this kind of argument would suggest. Notice in this argument, I never anywhere used the fact that I had a boundary CFT. The fact that this is the ADN Hamiltonian is a property of the bulk theory. Okay. And instead of this formula, I can write down other formulas that rely on the projector and the vacuum, but give you the same answer, which is that the time-band algebra looks like it captures all operators of the theory and has no commutant. Okay. And this is closely related, of course, to the fact that gravitational theories are holographic. Okay, just a second. Because gravitational theories are holographic, if you look at a set of operators in a time band, that in fact captures, or you look at a set of operators near the boundary, those also capture information of what is happening deep in the boundary. Okay? So this is related to the fact that gravity is holographic. It's in fact the manifestation of that. And therefore, you might have thought I could also end my talk here by saying in a theory of without gravity, the answer is simple. I get the answer explicitly in a theory with gravity. The answer is simple and it's trivial and there is no algebra you can define. Okay? But that's of course not going to be the one. Go on.
So let me ask this question
Yes.
using boundary CFT.
Yes.
So sometimes we consider CFT some sort of a theory on the boundary which doesn't have stress tensor but has conformal symmetry. There are various examples of such things, right? And sometimes people say that this is dual to system quantum field theory number, right? Which doesn't have gravitons.
That's like the first setup I mentioned. So if you think of the first setup, which was QFT without gravity, if you thought of a hierarchy of interactions,
Right.
where gravity was much weaker than other forces, it's hard to construct for example,
Right.
then indeed you would be able to define this time-band algebra. That's like the setup without gravity.
Right.
Now I'm saying what happens if you include gravity?
But in this setup also,
Yes.
you can talk about conformal dimension, various operators
Yes.
on the boundary.
Yes.
And that is like Hamiltonian.
Yes. It's like the,
Hamiltonian.
but that Hamiltonian is not an element of the time-band algebra.
Why is it not?
In this story of generalized free fields, the Hamiltonian is actually an integral over the line crossing time of AdS. Because this Hamiltonian, because there is no stress tensor. Right?
There is no
The
stress
fact that the
tensor.
stress tensor is an element of the time-band algebra, it comes from the fact that the integral T00 is there. No, but in
It
this,
could be that there is no stress tensor, but there is a charge operator.
no, that
which
charge
is,
operator that we try to write down in these setups, if this is the generalized free field setup, will be an integral over time So it will be an integral over time on the boundary over the time of light crossing over path. As you can see from the bulk setup, in a QFT, if you want to write down the Hamiltonian, you would have to integrate on the whole Cauchy slice in the bulk, which is the same as integrating on these boundary operators on a time of path. So indeed, if you look at the generalized free field setup, which is the one you're talking about, where the stress tensor decouples from the OP, then the Hamiltonian, the only way you can reconstruct it is by integrating on the length on the time path. Any other questions? Okay, so now the question is, of course, can we say something meaningful about this? Say, how am I doing on time? It's been 20 minutes or so.
20 minutes.
20 minutes. Okay, fine. Okay, so now I want to try and tell you, how it is that we will define meaningfully an algebra. So in fact, in a previous paper, Speranza, Jensen, and Sauce did define an algebra for this region and its complement. However, there's a subtlety in the construction. I think the answer in the end we find is correct. But I want, they did discuss this subtlety, but there is this subtlety, and I want to explain how you can get around this subtlety and define a meaningful algebra. So what is the physics of this? The physics of this that I want to emphasize, and this is related to your question you asked about whether there's some error in the proof. So there's no error in the proof. This is true, that the timeline algebra in the full theory has no commutant. And indeed, there is no way you can define an algebra if you want to define it, to arbitrary precision. So you should, I think the physics of this, which is kind of interesting, is that you should think of the holographic properties of gravity. And this is a feature of the holographic properties of gravity. Are a little bit like unitarity in ordinary QFTs. Okay, there's an analogy which I want to make. In what sense? In the following sense, okay? If we ask precise questions, then unitarity is important. It's important for us that in the end, the world that we live in is unitary, right? Forgetting about gravity, it's important for us that, physics is reversible. It's a fundamental property of physics. So if we ask very precise questions, if we ask, very fine-grained questions, then it's important that physics is always unitary. Similarly, in the theory of gravity, it is important that holography, gravitational physics is important. So, in particular, if you want to ask questions about the unitarity of black hole evaporation, or you want to ask, how did information about the infalling matter enter the Hawking radiation? And it's important that you have to recognize that gravity has these holographic properties. And if you try and argue, using semi-classical intuition about gravity and local algebras, you will run into paradoxes like the information paradox. So if you want to ask precise fine-grained questions, then holography in gravity and unitarity in ordinary theories is important. It is also easy to verify unitarity perturbatively. This is the exercise that we all do in quantum field theory textbooks. All of us have finished our postdoc. There are no PhD students here, but it's the exercise all of us did in QFT textbooks when we were asked, take an S matrix and show that this S matrix is unitary, right? Compute the one loop correction and show that it's consistent with unitarity. So we often check in perturbation theory that physics is unitary. Similarly, in fact, you can also check the holographic properties of gravity perturbatively in the following sense. As I said at the beginning, you can think of states about empty AdS and put various kinds of excitations in the middle, and you can ask, can you read off what the excitation here was by doing various physical operations in the boundary, and the answer to that is yes. So if you think of light states, remember, when you check unitarity in QFT, you're always checking unitarity about light states. And this is also true, you can also do this for holography. If you think of perturbative states, and you want to verify unitarity or holography perturbatively, you can do this. Okay, so this is another aspect of the analogy. So just as you verify unitarity in ordinary quantum field theories, you can verify holography. However,
these are gravitational states.
These are gravitational states. So you think of a state in the theory of gravity, you maybe put a red ball or a blue ball, you ask the operator at infinity to determine whether it's a red ball or a blue ball, and they can determine without waiting for light rays to emerge using gravitational physics. However, you can now ask, well, But in many everyday systems, unitarity is not manifest. For instance, if I roll this, this physics is obviously dissipated. This thing stopped, right? And so maybe the whole world is unitary, but unitarity is not manifest in many everyday systems. So there is a third regime, and the third regime is if you have a heavy background. Plus coarse graining. So it's important that when you lose unitarity, you always lose unitarity because you always coarse grain the set of observables. You choose not to keep track of some observables. So this leads to dissipation and alternately, to complete my analogy, it leads to approximately local physics. So approximately local physics is not holographic, so you have local degrees of freedom. And it's again the same setup. So what I want to explain is if you take a heavy background state and you coarse grain the set of observations, then just like you get dissipation in ordinary systems, it's also true that you will lose track of the holographic properties of gravity if you will get approximately local physics. So that's the reason even though we live in a theory of quantum gravity, we don't think of ourselves as boundary observers because we are making observations to some coarse-grained degree of freedom and we are living in a heavy background and therefore the world to us seems approximately local. Okay? So the resolution to this is going to be that we work in this regime where you introduce a heavy background state and you coarse grain your degrees of freedom, and that will tell you in that setup you can ignore this effect, and in fact you will be able to define an algebra for the time. Okay? So the resolution, the physics of the resolution, and this analogy I want to emphasize is that you should work in region 3. So this is why in all of these discussions, the observer, in these discussions of algebras, the observer is very important. The observer helps you. Okay, so this is just some philosophy, and now I want to explain.
So is it kind of similar?
Yeah.
I remember when you talk about this holographic information.
Yes.
And one consequence of the Hawking paradox.
Yes.
And Sandeep asked.
Yes.
And, of course, as an observer, I can imagine. Is it
Yes.
going towards that?
Well,
Is that how we want to?
of course, if you coarse grain your degrees of freedom, if you don't keep track of very accurate degrees of freedom outside, then the entropy of the radiation will increase. So of course you will lose unitarity. Physics is dissipated. That's the same thing here. So I want to explain how. So that's true. We know that. I want to explain how this phenomena will help you define an algebra for the time. Okay, so this is also the same thing because you see you need to lose holography to be able to define an algebra for this region and its community. So you need to do something that will make holography hard to see.
No, but I think the approach that you take in your earlier approach
Yes.
is that that's it. This is the holographic. I mean, you have an entire information.
Yes.
But
That's
now
it.
you want somehow.
Well, so you see,
Why do
if
you
you
want
want
to
to ask
define this?
precise
You can just
questions,
stop there. No?
so if you want to ask precise questions, unitarity is important.
Yes.
But in some cases, it's also important that we live in a dissipative world.
Okay.
I also want to explain this phenomenon. So it's true there's no paradox here.
Okay.
So it is also, if you tell me why is this not a paradox, I'll tell you unitary. Could you tell me, okay, explain what you see? So I also have to explain that. So that's so, okay. Okay, good. So there's no, if you ever ask any very precise question, this is important. Holography is important, but we often don't ask very precise questions. So I want to explain this construction the remaining 10 to 15 minutes. Okay. So
Suvrat, in your view,
yes.
can the black hole information possibly be explained within this approximation or?
No. Clearly we have to be in this approximation. Otherwise, if you want to ask a precise question about unitarity, then I think it's important that we should not be in this approximation. If we are in this approximation, it's like being in the approximation where physics is dissipated.
Well, that's true, but it's not ruled out that even within this approximation you may find an explanation of the information possible, right? What you are saying is that if you don't use any approximation, then there should be no information possible.
Yes.
But it could also be that within this approximation also there is a resolution, right?
Maybe, but within this approximation is where you get approximately local physics, and then these arguments for why information is lost seem to be valid. Okay, we can discuss that, but it seems to be that in those cases the arguments for why information is lost would be valid. You would really be able to define two different, if you can factorize the space-time effectively, which is what I'm now going to explain, then you will all of Hawking's arguments will be valid. Hawking's arguments really rely on factorizing the space-time. Okay, maybe there's, yeah.
So these efforts, recent efforts of explaining it using different saddle points of gravity, you would think of them as being resolving that within this approximation.
I'm not sure that they are doing something slightly different. They are, you add a bath and then they work in a rather precise setup. They don't work within this setup. In those setups, in fact, holography is important. And this is actually a completely separate discussion. So let's do it offline. But in those setups, you add a non-gravitational bath and you factorize things there. So those are precise setups. You are asking precise questions. There are some words that people say that are associated with those setups. That is, we can somehow get rid of the bath. Maybe those words would. I don't think anyone has ever made those words.
You are saying that you do, finally,
have precise factors.
Go back to the unitarity of the boundary system.
Yes, you always need that. The unitarity of boundary system is very important in all of these setups. So that's okay. Good. Let me just explain a little bit more now beyond the philosophy of how you do this. Yeah. So first, what is this heavy background state? In fact, although we use the word heavy background state, how are we doing on time 10? Okay. So even though we use the word heavy background state, what heavy really means is the following. We need a state psi which has the property that this is much greater than 1. 1 is the AdS scale. But in fact, that's all we need. It can be much smaller than n, which is the Planck scale. So it doesn't have to be, heavy as in very heavy. It doesn't have to be a black hole. So an example, if the cosmological constant in our world was of the opposite side, then a good example of a state that would satisfy this would be a virus. Okay? A virus is it could be an observer, because a virus is something that's much heavier than the cosmological scale, but much lighter than the Planck scale. Okay? So when we say we need a heavy background state, we don't actually need a state that back reacts or changes the geometry. That's why in response to your question in the beginning, I said we could be in global AdS everywhere, where you think of a background, but the background is not even classically back reacting. Okay, background is well below the classical back reaction limit, but it should be much heavier than the AdS scale. Okay. So in our world, as I said, think of a virus, which is parametrically larger than the cosmological scale, but parametrically smaller than Planck. Or not parametrically, much smaller than Planck scale.
The vacuum state is not of this type.
The vacuum state is not of this type. So about the vacuum, you cannot define these algebras. So these algebras do not, just like about the vacuum, physics is always unitary. Unitarity is very easy to see. To see dissipation, you have to introduce a background. Yeah, so you have to consider a state of this kind. The second property you'll need is that if you look at this, if I call this delta E squared, then delta E is also much larger than 1, but much smaller than E itself. So there also have to be fluctuations in the energy of this observer, which are again much larger than the AdS scale, but much smaller than the energy of the observer itself. So for instance, a black hole would meet this because it wouldn't meet this criteria, but it does have the property that fluctuations are square root n, which are much larger than 1, but they are much smaller in the energy itself, which is there. Okay, good.
Why do you require the fluctuations in large units?
We do need it, I'll explain it, but we do need the fluctuations. Okay, good. So let me now define how you define these algebras. Okay, so let me take this state psi and let me define, so let me define first the set of operators, the same set of operators that I have here. But here I cut off this n to be much smaller than S, where S is the density of states about this. Okay, so e to the S states about psi. Within this energy band. Okay, so there are some e to the S states, and so I cut off this set of operators for n smaller than S. So it's important once again that you have to coarse grain the set of operators. Okay? So you look at polynomials in these boundary operators, but you put a cutoff. You don't allow arbitrarily complex polynomials. This does not include the Hamiltonian at the minute. So as I said, the whole subtlety was how do you include H, and I'm going to explain how you include H. But for now I want to consider this set of operators, which is just a set which does not include H, and then I'll explain how you will add H back in. So consider a set of operators, but now cut off in this way, and define the following little Hilbert space, which is just this acting on psi. This A is a vector space because it's a span of all of these operators. So you act with this operator on all of these states psi, on this background state psi, and that generates for you some set of, so if this is the observer state, you generate some neighborhood of the observer state, which corresponds to exciting this observer state with these various operators. Okay? So I'll call that space H0. And you can also generate a family of states by first time translating the observer and then acting with these operators. This set of states is different from this set of states. Okay? And as a result of this property that the energy fluctuations are large, you can check that if you look at an element from, if you look at this matrix element, this side, this is very close to 0 if E is larger than 1 over delta L, which is this time. So provided this time interval is much larger than 1 over delta E, this overlap is very small. This is a little bit like the plateau that you were discussing, we were discussing yesterday. So it's the fact that there are lots of random phases here, and if I take this, if I take translate by some amount that's larger than 1 over delta E, then this overlap is almost there. So these vector spaces, if I take T to be much, gapped in intervals which are much larger than 1 over delta E, are almost orthogonal. Okay, so elements of this are almost orthogonal to elements of this.
So what is the approximation n much less than S? What is S?
S is the entropy, so the E to the S states about psi. So I restrict the number of observables that I have. If you like, you can take N to be much larger.
About psi meaning what?
Huh?
S E to the S states about psi.
This is the entropy of the density of states about psi. So you have the state psi, which is sitting in some, because you're already at very high energy, you can define a density of states.
At that energy?
At that energy,
Okay.
at the energy of state. Okay, good. So these vector spaces are almost orthogonal, and in fact, you can see that this, with some further assumptions on the state psi, if you look at the sum of these spaces for all t, the sum of these spaces takes on the form of a direct product times H0. So, or rather it takes on, so you get one variable which is just this time variable, and then you get, the original Hilbert space that you have. Okay. So the direct sum of all of these Hilbert spaces gives you an additional degree of freedom, which you can think of as a time degree of freedom, together with all of these excitations that you were making without introducing the Hamiltonian. Okay. And this degree of freedom is the time degree of freedom. In fact, you can define a time operator by defining a projector. PT is the projector onto HT. In fact, you have to smear this operator a little bit. I won't go into that. And then you can define a time operator. So this allows you to define a time operator. Notice that all of this construction would never work if psi was the vacuum. If psi was the vacuum, then e to the minus ist on psi would also be the vacuum. Okay. So you cannot define a time about the vacuum. But when you have a heavy background state, you can define a time operator. As you can see explicitly just by defining these states, by defining these projectors, using the fact that these projectors are almost orthogonal, and then you can define a time operator this way.
So why can't you do that? I mean, A and
This?
No, I mean, why can't you define HT to be e to the minus IHT?
This is the same. If you are the vacuum, this is the same as the vacuum. This is trivial.
Why can't you define it? Why can't you evolve it later?
Or you could evolve it later, but that's actually the same space if you're under certain conditions on psi. If you act, so this is a version of the Riech-Leader theorem. It's the fact that the action of operators at a later time is the same as the action of operators at an earlier time. So it doesn't matter whether you evolve earlier or later. Huh?
You don't get that orthogonality in particular?
You don't need the orthogonality.
You don't get that orthogonality in particular?
You will not get that orthogonality. The action of operators at later time over the vacuum is the same as is dense in the space of operators of action at earlier time.
No, but with all these approximations, would that still hold?
If you're in the vacuum,
Yeah.
no, nothing. If you're in the vacuum, you act with operators at this time or at this time, it gives you the same space of things. Which is obvious also from here because acting with this gives you vector. But even if you evolve later, it doesn't matter. That's like acting with operators at a later.
Yeah.
You'll always get the same set of states, whatever time plan you choose. This is the Risch-Leiter thing, I can prove to you.
No, but Risch-Leiter theorem, would that be applicable
About the vacuum it is.
under the approximation?
Yes. The approximation here was only coarse graining. The Risch-Leiter theorem only requires positivity of energy. So it would be. Okay, good. So you get this additional time operator which you are able to
Because can you
define.
just explain again? So what is the property of psi that you are demanding? It's not an energy eigenvalence. It has to have fluctuation.
Yes, it has to have fluctuations, and so these times have to be orthogonal to this property. That this overlap is very close to zero. This allows you to identify a time operator, which is this operator, because these states are almost orthogonal. So this is the property of psi that you want. That time evolving it gives you an orthogonal state. So therefore you can use that state as a clock. Okay. You can also PT is a projector onto HT. Actually, PT is a projector onto HT with some coarse graining, but I won't explain that.
So we have one
Between
question.
HT and T plus delta.
That
Yeah.
small a is what is small a?
Any element of this act.
So it's just a number. Is that correct? Or
It's an operator. It belongs to this.
I mean, can it act on psi and
It can
come
act on
out
psi.
as a number?
It can act inside, but you'll always get orthogonality.
Okay. And as you increase capital T, if
Yes.
you evolve it further and further,
Yes. Eventually, you will run into trouble because you'll get Poincare recurrence. So you will, but if you're within a large band of T, you won't.
so what determines, the upper limit of T?
The upper limit of T will be determined, I think, by this S. It's a question of what is the Poincare recurrence time. Eventually, you'll get. So it depends on how precisely you ask things. This is approximately zero. In fact, these overlaps are e to the minus s by 2. So if you want to ask very precise questions, you will run into those overlaps.
So you are saying that the system may come back to itself after?
The system may come back to itself, and even if it doesn't come back, it's not exactly orthogonal if you keep track of these corrections of e to the minus s. Yeah. Okay, good. Sorry, I'm running out of time, so let me just explain quickly. You can also define a Q operator, which has the property that Q hat is equal to I minus I. Okay? But Q hat on A is equal to 0. This Q hat is like an operator that time translates the observer but doesn't do anything to these operators. So it doesn't act on these operators, but it time translates this state. So you can think of this Q hat as some coarse-grained version of the energy. Yes, just 5%. Some coarse-grained version of the energy, which measures the background energy, but doesn't measure the energy of the fluctuations about the background. So this Q hat you can think of as a coarse-grained energy. Okay. Okay, good. Let me now just explain, how you define how you define this algebra. And I'll stop. Just give me a few minutes more, please. So the key idea is, rather than using the original operators, you deform the operators. So how do you deform the operators? So you deform the boundary operators in the following way. You define hat of O of tau as the integral. I can't explain all of the details of this formula right now, but this PT is this projector. Okay, this PT you can think of as the projector on this one-dimensional Hilbert space. Okay, so you write down this operator, which is not the original operator that you had, but some deformed version of the operator. This operator has the property that if you act with hat of O of tau on psi, it gives you O of tau on psi. But you can check that if you try to evolve this operator with the Hamiltonian, then in fact it gives you the hatted version of modular evolution. So this operator has the property that if you just act on the observer state, it looks like you acted with the original operator. However, if you try to evolve this operator with the Hamiltonian, it doesn't evolve it out of the time band, rather it is as if you did modular evolution to this operator. Okay. I can't prove these formulas right now, but they're pretty easy to prove if you start with this. These kinds of, so this operator is like a version of dressing, where you have dressed the operator to the observer in such a way that if you try to evolve with the Hamiltonian, you don't actually evolve out of the time band, but in fact you just do modular evolution. These kinds of formulas have appeared previously in the literature. They also work that we did with Kyriakos several years ago, when we constructed operators in the black hole interior, and also more recent work by Kyriakos and collaborators. And so these kinds of operators have appeared in the literature before, and are the standard way to, when you have a background, to dress operators to the background to get operators which are insensitive or transform in some way under the boundary Hamiltonian, which is not the way the original operators did. Okay, now the last thing I want to tell you is how this is the same as what's called the gravitational cross product, and then I'll stop. So this is older formulas, and now I just want to write this formula in a way that will make apparent the relationship to this cross product about which a lot has been said recently. And then I'll stop. Okay, so in particular the algebra that you want here, the correct answer for the algebra is, you think of the span of all of these operators, but hatted, and then to this you add e to the IHX. So this is now an algebra, it's closed under products. You can take products, and now the Hamiltonian is no longer evolving out of the algebra, it's evolving you within the algebra. However, let me explain how you can write this in the form of the cross product. Let me define the unitary operator. This t hat is the time operator, this q hat is the conjugate to the time operator that I defined. And now this is a unitary operator. Notice h minus q hat actually commutes with t hat. You can check that this formula that I wrote happens to be the same as defining hat of O hat tau. And I can't explain again, can't derive this. Just a conjugation of O hat tau with this particular unitary operator. So this formula that I wrote down, that looked, that said you insert some projectors, the way this formula was working was, you were trying to measure the time by inserting these projectors and then making the operator act at a particular time. This formula looks much more elegant, but in fact you can check this formula is the same as this formula. Okay? So this algebra that I've written down, in fact just looks like the algebra of these operators evolved with this unitary operator and e to the IHX. In particular, you can look at a unitarily equivalent representation where you unevolve these operators with v, you take the v and you move it to this side. Okay, so you have an algebra, but now I can think of a unitarily equivalent representation by just conjugating all elements of the algebra with v dagger. Okay. If you do that, the unitarily equivalent, and this is the last thing I'll say, representation you will get will just be the original algebra of operators that you had okay, and v dagger e to the IHX v. So when I conjugated with v dagger, I got the original operators in the time band, but now I've changed instead of deforming the operators, I've now deformed the Hamiltonian. And you can check, and it's very nice, it turns out that this just turns out to be e to the IQX times delta to the minus IX. So for those of you who are familiar with the cross product, you will notice that this algebra has precisely the structure of the cross product because you have a set of operators that belong to the time band, which was a QFT algebra. And then with the QFT algebra, you have added this additional degree of freedom, this Q hat, which translates a time which has nothing to do with this algebra. And then you have coupled it with this modular operator. So you have coupled the movement of time in this auxiliary Hilbert space with this modular operator. Okay. So for those of you who are not familiar with this, I don't have time to go into this right now, but this structure, the algebra written in this form, is precisely the cross product. And this cross product has various nice properties because it allows you to define a trace and allows you to define entropies and so on. And so, there's this nice relationship between these older formulas that we use to dress operators to your background and these formulas for the cross product, which arises by recognizing that in fact the older formulas can be written in this form, and then some unitary transformation maps you to the cross product. Okay, so I will stop there. I already went a little over time. I'm happy to ask more questions, answer more questions, but let me just summarize what I said. The main point of this talk was that if you think of the algebra of the time band, there's a subtlety in defining the algebra of the time band. You cannot define the algebra of the time band about the vacuum. But you can define the algebra of the time band if you introduce an observer. The observer just means a state, a background state, which has energy which is large compared to cosmological scale. But you can also take it to have energy much smaller than Planck scale, which also has large fluctuations in energy. This background state allows you to define some effective Hilbert space that allows you to introduce an additional degree of freedom, which is the clock. Okay? And then this clock allows you to define these operators in the time band that are dressed to this background, that under the action of the Hamiltonian don't move out of the time band. Okay? And if you do a unitary transformation, you can see that this in fact turns out to be the same as this cross product that has appeared in the literature. And in fact, this was the answer that Jensen, Speranza, and Sorsay guessed, although without going through all of these subtleties. But this was indeed the answer that they found. Okay, so there's this relationship between this older literature and this newer literature, which I think is very nice. And I could say more, but let me stop here since I'm already out of time. Thank you for your attention.
So one question, in the cross product story, is there this truncation of operators?
In the cross product story, no. In the cross product story, what people say is you think of this algebra and you just think of going off to infinity, and then you get the quantum field theory algebra.
Right.
And then you introduce an additional degree of freedom that corresponds to this Q hat, which is this time degree of freedom. And then you couple its action with this modular operator, and that gives you the cross product. That's how the cross product is introduced. Now what we are saying is, the way to really think of it is, first you truncate the set of operators, then you define, these rest operators. To do that, you have to do all of these truncations. After you have done these truncations and these deformations, you can later then take the limit to infinity. Or you can take the limit of these operators to infinity while always preserving the hierarchy that this n is much smaller than capital N and is much smaller than S. Instead, alternately, you can think of formulas with this set of operators where you ignore effects that are suppressed by 1 over delta E or 1 and 1 over E. So we are always working in a constrained approximation, but after constraining you can then also take the continuum limit, and that's the limit in which you get the algebra. What I say was not clear? Or?
No, I'm just trying to see how is it, how is it exactly equal to the cross product motion where there is no notion of truncation, no notion of...
There's no notion of truncation.
Just complete the algebra. And then
correct. So initially I start with a set of operators, which are actually not even an algebra, where I've truncated the operators. Then, I write down these formulas. I can write down these formulas even with the truncation. You're right that to get an algebra, I later need to take the limit of this n off to infinity. I need to get rid of this limit I had in a set of products of operators.
Yeah.
But I can do that provided I take the limit in a way where I keep n is much smaller than s is much smaller than n.
But then it's not an algebra.
It is an algebra because I've taken n to infinity. So it's an
In
algebra.
a limiting sense, it is not an
In what?
algebra. In a limiting sense, you have to stop at some point.
In a limiting sense, it is an algebra because now I take all of these guys to infinity in this order. So now I take this to infinity, then I take this to infinity. Then I take
Why are you taking S to S? S is not under your control, right?
Well, it is because it's the energy, right? So I take the energy of the state to infinity.
No, but I thought energy is some fixed. You gave me this.
No, but I can take the energy to be say square root n. And then I take a limit of states where the energy of the state goes to infinity. So to get an algebra, I'll have to do this. To get an algebra, I'll have to take a limit of states where I take square root n to infinity. Or alternatively, you can say you work with this set which is not an algebra, but then you ignore the fact that there are some products which take you out. So this is how we always have to do.
Is there a discussion of this sort in the cross product story?
No, there's no discussion of this sort of. In fact, we are also not adding much to this discussion. This is a subtle question of how you think of, sets of observables which are not algebras. So there's an issue of edge effects. What happens, how do you close this algebra under this usual product? That's a slightly separate discussion from the discussion I wanted to have here, which is how do you include the Hamiltonian, which is a leading order in G Newton effect. You just see it immediately when you include the Hamiltonian.
Yeah.
There's an additional issue of what happens with these edge effects, which actually has not been dealt with very satisfactorily.
Edge effects, but just the fact that it seems very crucial that you're truncating the set.
Yeah,
truncating the algebra to a set which was much less than the.
It is true that was important, but I think it should be, and you're right, actually this is something that should be worked out more carefully and has not been worked out. I think the word we would like to say is that, after you have done this truncation and produced this algebra, you later take all of these things off to infinity and you forget about the fact that you have done the truncation. Okay, but you're right that this should be done more carefully, which no one has done more carefully.
Yeah. So suppose we are interested in flat space, right? Where you really want to take n to infinity.
Yes.
So then, is it possible that this will become exact in that level?
You want to take the cosmological scale off to infinity. Oh, sorry.
Yeah, so
cosmological scale is-
asymptotically flat space time, right? I want to you start from AdS and then go to the flat space limit, right? Then capital N you are taking to infinity anyway, right? In that limit.
Yeah.
So is it possible that this becomes exact?
Yeah, this one, of course, was not just the one of the AdS, it was also the one that corresponded to the energy of these operators. So, you wanted the observer, there's a physical statement here, which is you want the observer to be much heavier than the set of experiments that you're doing. So, you're doing some set of light experiments which you're trying to use to define an algebra, but you want the energy of those experiments to be much smaller than the energy of the observer. So, you want the observer to act effectively like an infinite energy bar, where the experiments that you're doing don't see the observer's energy, finite energy. That's why you're able to define a time operator. Usually, why can't we define a time operator in quantum mechanics? Because the Hamiltonian is bounded below. But what is happening here is that the observer is acting like a bath, and therefore you're being able to define a time operator because you're not seeing the fact that the energy is bounded below. So in flat space also it would be, I think, the same setup, which is that you would define a physical energy which corresponds to the energy of the experiments you're doing. So you're right that the infrared cutoff in some sense has gone off to zero, but you still want to introduce a physical cutoff corresponding to the experiments that you're doing, and you want the observer to be much heavier than those experiments. And when you start including those effects, then the whole construction will break down. So you always have to be in a limit where the energy of experiments you're doing is much less than the energy of the observer.
Suppose the observer is the matter that is there in the universe, which is of course has very large energy, right?
Yeah. It has very large energy. Then you would be able to do this to as good an approximation as the total energy of stuff in the universe.
So if the spatial slice was infinite,
Yes.
and let's suppose it's equal to cosmological concept,
Yes.
right? Suppose the spatial slice was infinite,
Yes.
and you have dark matter in the way we know, or even ordinary matter. Right?
You mean the total energy in the universe is infinite?
Yeah.
Then it would become exact.
Then
But when we prove these results of holography, we always have to work with a set of states where the total energy is finite, I think. If the total energy is really infinite, then you would be, so even if the universe is asymptotically flat, we would still like to work with a set of finite energy states. And then this thing would be valid up to the approximation of your energy of experiments divided by energy of total energy of matter.
But you are saying if you are using really the cosmological setup where there is a total infinite energy in the universe, then this would be exact.
No, sorry, I didn't understand. Why?
Just ordinary matter, right? I mean, which fills the whole spatial slice.
Just ordinary matter which fills the whole spatial slice, but so you mean the total universe doesn't have finite energy?
Yeah, some
Then maybe you could define exactly local operators, but wouldn't we like to work in a universe even asymptotically flat space where you really have finite energy when you define the S matrix and so on? If you are in this setup, you would also.
But in our universe, it's not the case, no?
Well, our universe might have total finite energy.
If the spatial slice is
Even if the spatial slice is compact or at some point homogeneity breaks down, or yeah. If, by the way, if let me just say one thing, if the universe has total infinite energy, then of course unitarity would also not hold, because you could always dissipate into that universe. So unitarity would also not be a statement which would be meaningful. So many things would break down. Conservation of energy would not be a statement, and unitarity would break down. So okay. So to the extent unitarity is exact, holography is exact, but yeah. You could say dissipation is really true in that universe. It's genuinely dissipated. It's nice to think of a universe which is not dissipated. Okay.
But our universe is not like that.
Well, I think our universe might be like that, but okay, we don't know is the answer, right?
Okay.
Okay. Yeah.
So maybe you already answered it
Yeah.
in Abhijit's question, but I was just wondering, so you were mentioning, and I had heard that before, that the cross product, in a cross product, these entropies are well defined.
Yeah.
Is that possible?
How does it happen?
How do I see that, for example, from this construction?
It requires more work actually. Thank you for the question. It involves the fact that you can define a trace in the cross product. So originally, when you look at these operators, let me call these operators, trace of A is infinity. These operators don't have a well-defined trace. However, it turns out in the presence of this cross product, if you work with a state which has the form f of t to the minus I of t inside, not the original state, but some superposition of the observer time translated in different ways. You take this as a background state. Then in this background state, it turns out that if you look at the modular operator for the operators with this cross product, like you look for the operator S plus X psi is just log of this delta. So if you ask for the modular operator that reverses these two operators, that's what the modular operator does. It puts this operator to right and this operator to left. Okay. So if you ask for this operator, which is not the same as this operator is the modular operator about this state f, then this operator takes on the following form. It turns out that this operator delta hat looks like f tilde of f psi plus q hat squared with f tilde of q hat squared into e to the minus, sorry, I'm going to write the continuation of this formula. Okay, the virtue of this formula is the modular operator factorizes into an operator which is an element of the algebra, which is just a function of h psi plus q. So this guy into this guy, and an element which is the commutant of the algebra, which is just a function of q, which is this guy and this guy. When the modular operator factorizes in this way, so the modular operator has the property that you can think of it as the density matrix cross the inverse of the commutant. When the modular operator factorizes in this way, you can define a trace by just defining the trace of the expectation value on the state rho to the minus half of operators. So you get a density matrix that gets regulated by the presence of these additional degree of freedom, and you can use that to define a trace. So it's not obvious from what I said that you could define a trace, but you can define a trace of the cross product using this. Maybe one point to make is the following. There's been a lot of discussion about how in these cross product formulas you get this area term. In fact, this area term is not seeing the background density of states at all. If you go through this construction carefully, this cross product is only seeing this effective Hilbert space that I defined by thinking of experiments I could do about the observer. It will never be sensitive, and for this Abhijit's point is important, it will never be sensitive to the background entropy of states that you have. So this area term that you're seeing is really a fake. It's really, just some relative entropy between states, and you're really only sensitive to the entropy of the effective Hilbert space that you define. And you're never going to be sensitive to the UV complete entropy. So the fact that you see this area term is not very deep, it just comes from the equations of motion. And it's really just seeing the entropy of this effective Hilbert space, not the UV complete space. So you can define traces and entropies in the space, and you have time to go into that. But I can explain to you more. What I said right now was too quick.
So just for the discussion, so that I asked this question. So this story will not be related then to renormalization of the Newton's constant.
Yeah, that's a good question. So how is this story related to renormalization of Newton's constant? It is not clear to me, in fact, that the cross product is immediately obviously related to renormalization of the Newton's constant, which is a dynamical effect. The fact that you are able to define this trace in this setup really has to do with the fact that you have this additional degree of freedom that you have smeared operators over, and by smearing operators in this additional degree of freedom, you get operators that are slightly smoother than your original operators. It's like the analogy I was giving you in the bus. Let me just say to others, sometimes if you try to define an operator in quantum field theory and you smear only in space, you find that you can't get, the operator doesn't have finite fluctuations. For instance, if you take the stress tensor and smear only in space, you will find an operator that doesn't have. But if you smear in both space and time, then you will find an operator that is smoother. So here you introduce this auxiliary degree of freedom, and by smearing operators in this auxiliary degree of freedom, you found that you were able to define a trace in entropies. But it's not clear that there's anything dynamical about this. The renormalization of Newton's constant really comes from taking a QFT, doing a one-loop calculation, which has to do with interactions, and showing that there's some arguing about some dynamical effect. This really is a kinematical thing, which is you're kind of smoothing out the trace by introducing an additional degree of freedom and using analytic continuations and so on. So my feeling is that it's the story that the Newton's constant gets renormalized in the same way as fields, as the entanglement entropy of the fields, might be a more interesting story than this story of the cross product, which might just be a kinematical way of defining the trace. Ronak has come back just in time to answer the question.
I have 2 comments about this.
Okay.
One was exact question for reply to that.
Okay.
Okay, so first of all, I agree with your broad feeling because this does not require Newton gravity or Newton constant anywhere. You could have just defined I guess I'm calling it T. You can just define L2 of our Hilbert with an operator T and use that to do the entire thing. So like somehow gravity is not really coming in any obvious way.
But in the beginning there was a quite contrast that he emphasized between gravity and
It did come in. Yeah.
somewhere.
But in the end, it's not coming in here. You introduced this time variable. You had to introduce this time variable in the area of gravity.
Yeah.
You're right that without this time variable, the operators were kind of not defined.
Yeah.
But there's no dynamical G Newton that's appearing.
Yeah.
It's not like you're computing anywhere at 3-point any interaction or something. It's the fact that there's this constraint that you get out of this constraint. So,
So second comment is that actually this denomination of Newton's constant theory might also not be that easy. Okay, because what is the story? The story is that when you put the theory on the cone, the denomination of Newton's constant away from the cone is the same as the denomination at the cone point. Okay. The point is that the correct one calculated entropy was never the cone, because Newton's constant is smooth everywhere. Okay. And in fact, there are theories where there is a difference between these two calculations and like Poppler makes world-like terms of entropy.
okay.
And so that is also not like there is a denomination of Newton's constant, but it's not dynamical the same way around.
It could be, and actually Ashok also says this many times, which is that sometimes when you renormalize the stress tensor, that renormalization also you put into renormalization of the Newton's constant. You often add local terms when you compute the stress tensor, and you renormalize everything into Newton's. So Newton's constant bears a lot of weight, poor thing, of various renormalizations, and maybe you can't renormalize everything consistently, the entanglement entropy of stress tensor. So maybe this idea just doesn't work.
Yeah, I think that there is in general a world-like term in the general equations.
But that's a different issue. The question is that it's consistent that the renormalization of Newton's constant can remove divergences in the stress tensor, can remove divergences in entanglement entropy, can remove all these different divergences together in the same.
I'm saying there is no remove divergence in entanglement because the entanglement entropy calculation is always around like it's an approximation which works on.
Was always an approximation.
Because like the entanglement entropy calculation comes when you try to calculate black hole entropy by putting the replicating the black hole spacetime and creating a conical singularity, which is not the correct calculation. It's a wrong calculation.
Or it comes when you compute any entropy, then you'll get a divergence, a QFT divergence in the end.
In gravity, you have to replicate the boundary conditions, not the bulk gravity.
QFT, right?
No, but in gravity, you don't replicate the bulk gravity, replicate boundary conditions. Bulk stays smooth. So there is no issue about
the boundary entropy will have a divergence if you take some, entangled finite region.
Yeah, but it's not a.
So the way I
First
understand
not
it,
black holes.
But
yeah, I
okay.
understand it. If I take a thermoplastic and if I think of the bulk as some quantity, then ask for some sort of a entanglement entropy, then there will be a divergence associated with just the UV degree of freedom.
Neither way.
Near the lines.
Yeah, but I
But
think that
given that it's a theory of gravity, the right way to do that would be to compute it from the boundary Nernst formula,
Yeah.
which is just a finite area.
Yeah.
And that finiteness you understand as absorbing that infinity into the
So that is the usual sustainable story.
But here there is no, it doesn't use any sort of replica trick in the boundary.
Varying beta as a replica. And that's what you usually do to extract an entropy. 1 minus d by dt. 1 minus beta d by dt. Right? And the point is you it's always smooth in the bulk, so it's never an entanglement calculation in the bulk. It's just that in some cases, there is a part which approximates an entanglement calculation, but there could be other parts also which do not turn up in some minimally coupled cases, but will turn up in the higher derivative theory.
In Gibbon-Shocking, there is never any singularity in the form.
That's exactly what I'm saying. So the entanglement entropy interpretation of the subleading parts of Gibbon-Shocking is an approximation.
Yeah.
So,
But you can do subleading part of Gibbon-Shocking without doing entanglement. I mean, you can just calculate the one loop return,
That's
right?
exactly
And that's perfectly smooth.
yeah, that's what I'm saying. There's only one time the denominator actually needs to be given, which is when you get the stress tensor, what you call it stress tensor.
Okay. Anyway, yeah, but in this case anyway, my feeling is this cross-product story is not a very dynamic story and not sensitive to the It's not like it's going to be decided for the black hole. It's not sensitive. So the area term I didn't have time to explain, but maybe it's taking. So we'll just try to do the equations of motion.
If there are no further questions, thanks for the